Hello everyone. So this lecture we will discuss about propagation of elastic wave in continuum. That means we will discuss about unbounded or infinite medium. Earlier on the previous class we discussed about finite medium like a striking bar hitting a long cylindrical bar. So the equation for that we derived as partial of u, second partial of u with respect to time is equal to Young's modulus rho and divided by rho, second partial of u with respect to x2. So this is for finite medium like split Hopkinson pressure bar SHPB. So which is in this case it was uniaxial stress. This is what we discussed in the last in the previous lecture, and then the velocity of the wave, that longitudinal wave, we found out to be the square root of the ratio of Young's modulus divided by density. So now in this lecture we will discuss about the equation for propagation of elastic wave in continuum, which will denote which means unbounded or infinite medium. So let us consider a body and a unit cube in the body. So this is the cube. We have the coordinate axes x1, x2 and x3. This unit cube has the length of the sides are delta x1, delta x2 and delta x3. So now the stresses acting on this unit cube are, we can see face by face. The first will be, if we say the front face, this face, are sigma 1 sigma 2 and sigma 3 So this is the normal stress and these are the shear stress. Similarly, if we see the stresses in this phase, on this phase it will be sigma 2 is the normal stress and others are shear stress. And similarly the third phase on the top, it has sigma 3 as the normal stress and other two are shear stresses. So we are not going to discuss about the concept of stress. I am assuming that all the students have already studied about stress at a point, and in this the stress components, the first suffix, suppose we are writing as sigma 1 2, so first suffix will tell us the direction of stress, and the second suffix will tell us the plane on which the stress is acting. So if you see here sigma 1 2, so the direction of stress is 1 along this x1 direction, and then 2 is the second suffix will give us the plane. That means that plane is, this plane is perpendicular to or normal to x2, so that 2 is the second suffix. And under equilibrium, so we are assuming that this case is a quasi-static case, let's say, and we think that this is under equilibrium. So under equilibrium, the forces are the summation of forces will be equal to 0 and summation of moment will be equal to 0. So these are the x1, x2 and x3 are, as you can see, the different 3 different coordinate axis directions. So under equilibrium, the static equilibrium conditions, so we will get summation of forces equal to 0 and summation of moment equal to 0. And these planes are, as you can see, these planes are in the unit cube are taken as the normal to the coordinate axes x1, x2 and x3. And if you want to get the forces on the other faces, here we are showing only 3 faces. If you want to get the force on the opposite faces, let's say we have a right side face is this one, and then if you want to take on the stresses on the face on the left hand side, so this face, then the stresses will be equal on that face. So these are equal on that face if you compare this face and this face. However, if we go for a dynamic case, so we do not have any static equilibrium. So we have no static equilibrium. So we cannot assume like the case, the previous case. Now what will happen is there will be a variation in the stresses of this face and that face. So now we will see that we will assume at the center point of that unit cube, and this stresses are sigma 1 1, sigma 2 and sigma 3 3 here. So if you see in the front face now, this front face, so the stress acting here are sigma 1 1 plus half of, I'm sorry about that. So these symbols are all somehow mistakenly taken as this. These are all partial of sigma 1 1 with respect to x1. So because this is our delta x1, this is delta x2, and this is our delta x3. So similarly, if you want to talk about the backside plane, so the sigma will vary. So this sigma and this sigma, so if you see there is a difference. So this term half of partial of sigma 1 1 with respect to x1 delta x1 means the variation of stress when we move from center point to on this front surface. So this means the the variation. And similarly this has a negative value, the same term with a negative value, that is in the negative direction. So similarly, if you want to talk about the stresses on this face, right hand face, and the left hand face and the right hand face, so this will be this one, and here this one, all of these were a mistake. So these are all partial derivative, and similarly on the top and bottom face we will get the similar trend. We will get the similar trend. So now we will because this is, we are talking about a condition that has no equilibrium, no static equilibrium. So we will use the Newton's second law. So basically, to get the elastic wave equation, for elastic wave equation, so we want to use equation of conservation of momentum. For shock wave, later we may discuss about that. For shock wave we may need conservation of mass and energy as well, but in this case, so we will go with the equation of conservation of momentum. So if we have these Newton's second law, the force is equal to force in three different coordinate axis directions are equal to mass into acceleration in that direction. We can have in one direction, let's say in x1 direction only, x1 direction, this direction in the figure, the x1 direction. So summation of forces in the x direction will be equal to mass of this unit cell, which is density into volume, and multiplied by the acceleration x1 along x1 direction. So this is, so we are applying the Newton's law along the x1 direction. So if we want to have the forces, now we want to have the forces. In the previous slide we have seen that there are stresses. These stresses are on the faces. That means actually stresses are defined at a point that is at the center of the faces. So the stress, this one, or maybe this one with a negative sign, if you find in whatever you found in the previous slide is a negative one, because we have a negative here, that's why we use the positive sign here. So this one and this one is the stresses at the center of the face. Stresses at the center of the face, suppose the front face, and if you want to know the forces along this direction, then what we need to do is we will multiply the stresses with the area. So this is the area of this area along x1 direction, area along x1, and that is the resultant force. So we have resultant force in x1 direction, we have resultant force in x1 direction. Sigma 11 and sigma 11 here from front face and the back face, and then similarly sigma 12 and sigma 12 from the left hand side phase and the right hand side phase. Similarly, sigma 1 3, sigma 1 3, this entire term actually, sigma 1 3 this term and this term. Similarly, in the second case also this term and this term. So this term is on the right hand side phase and this term is from the left hand side phase, and then and the second last term, this is on the top phase, and then the last term of the stress is from the bottom phase. So now we multiply the area and then that is equal to the summation of all the forces, resultant forces in x1 direction. So we want to simplify this equation. Now what we will do is we want to simplify this equation. How we will simplify? So we know that this sigma 1 1 and sigma 1 1 will cancel out, sigma 1 2 sigma 1 2 will cancel out, sigma 1 3 and sigma 1 3 will cancel out. So this will give us, so what we did is here simplifying partial of sigma 1 1 with respect to x1 multiplied by delta x1 delta x2 delta x3 plus partial of sigma 1 2 with respect to x2 so multiplied by delta x1 delta x2 delta x3 plus partial of sigma 1 3 with respect to x3 delta x1 delta x2 delta x3 is equal to rho delta x1 delta x2 delta x3 and second partial of u1 with respect to t. So now if we simplify, we can cancel the volume term, and that will give us partial of sigma 1 1 with respect to x1, partial of sigma 1 2 with respect to x2, partial of sigma 1 3 with respect to x3, which will be equal to density rho times second partial of u1 with respect to time, and similarly for other two directions, sigma 2 1 x1 partial of sigma 2 2 with respect to x2, partial of 2 3 with respect to x3 is equal to rho second partial of u2 with respect to t, and partial of sigma 3 1 with respect to 1, partial of sigma 3 2 with respect to x2, partial of sigma 3 3 with respect to x3, and rho multiplied by second partial of u3 with respect to time. So these are the three equations we are getting, and these three equations in indicial notation, we have not discussed about indicial notation, by the way. If time permits, we will discuss that in a subsequent lecture, but some of you may have already some knowledge of indicial notation. So we will I will show you how we can express it in indicial notation. It's sigma partial of sigma subscript ij with respect to xj is equal to rho density second partial of ui with respect to time. So that is called in indicial notation So these are easier way to express equations like this. So we can discuss this later. But even if we don't use the indicial notation, we can work out this derivation. So these three equations can if we can solve, and it will give the equation of elastic wave. So we will be working on that, and for that, by the way, the stresses need to be replaced by strains. We will see how to do that. So now for generalized Hooke's law, for an isotropic elastic solid in a triaxial state of stress, it is not uniaxial, triaxial state of stress can be expressed with these equations, like sigma subscript 1 is lambda delta. I will tell you what these symbols means, twice mu epsilon 1. Similarly, sigma 2 is lambda delta twice mu epsilon 1 and sigma 3 lambda delta twice mu epsilon 3. Oh sorry, this one is 2, and similarly the shear stresses 1 2 is equal to twice mu epsilon 1 sigma 1 is equal to twice mu sigma 1 sigma 2 equal to twice mu epsilon 2 I am sorry, this 1 3. So here the delta is nothing but epsilon 1 plus epsilon 2 plus epsilon 3 and it is called as dilatation, and both lambda and mu are Lami's constant. So they are the material constant. I will tell you later the relationship between lambda and mu with Young's modulus and Poisson's ratio. So these 6 equations are generalized Hooke's law, and then we will be using these equations in our previously found equation. So whatever we found earlier is partial of sigma 1 with respect to x1 plus partial of sigma 1 with respect to x2 plus partial of sigma 1 3 with respect to x3 is equal to density multiplied by second partial of u1 with respect to time. Now if we substitute these stresses with strain, what we get is partial of lambda delta plus twice mu epsilon 1 with respect to the whole thing, the partial derivative of whole thing with respect to x1 plus partial of twice mu epsilon 1 2 with respect to x2 plus partial of twice mu epsilon 1 2 with respect to x3 is equal to rho second partial of u1 with respect to t, and if we simplify more, partial of lambda multiplied by delta with respect to x1, then twice mu epsilon subscript 1 1 x1, sorry there will be partial sign here, plus twice of mu partial of epsilon 1 2 with respect to x2 twice mu. So as you can understand, the mu is the constant, material constant, so that comes out of this partial derivative, and that will be equal to rho per second partial of u1 with respect to t. Sorry, I have mistakenly written this as epsilon 1 2. This should be epsilon 1 3. Here also it should be epsilon 1 3, not 1 2. Then the whatever expression we found in the previous slide is this one. So we will use the definition of strain to convert these strains to displacement. So the definition of strain says epsilon 1 1 is equal to partial of u1 with respect to x1. Then similarly the shear strain epsilon 1 2 is half of partial of u1 with respect to x2, partial of u2 with respect to x1, and then epsilon 2 1 3, sorry, we are talking about only x1 direction now. So half of partial of u1 with respect to x3 plus partial of u3 with respect to x1, and then if we substituting on the above equation, this equation, then we will find that partial of lambda delta with respect to x1 plus twice mu now we are replacing the epsilon 1 1 with displacement, and that is with respect to x1 plus twice mu partial of the whole thing, half of partial of u1 with respect to x2 plus partial of u2 with respect to x1. Then the third term will be twice mu will be half of partial of u1 with respect to x3 and the partial of u3 with respect to x1, and will be equal to rho second partial of u1 with respect to time. So now simplifying more, the first term will remain same. The second term we can simplify as, the second term we can simplify as second partial of u1 with respect to x1 plus second term, the first, this will not be 2. So from this term we get mu second partial of u1 with respect to x2, and then from this term we can get mu second partial of u2 x1 with respect to x1 and x2, plus from this term mu second partial of u1 with respect to x3 plus mu second partial of u3 with respect to x3 and x1, which will be again equal to rho multiplied by second partial of u1 with respect to t. So now we will be using an introducing an operator nebula 2. So this is the operator, and this is with indicial notation. We will not discuss much, but this indicial notation, if you see, there are two i's here that shows the summation is implied. So these repeated index shows summation. So we can discuss this later if time permits, but without this indicial notation we will be working out. So in the previous slide, so we ended up with this one, and so we'll start from there. So here, so if we use the nebula in this part, so what it will give is lambda partial of delta with respect to x1 plus mu double partial of u1 with respect to x1, and then mu the operator with u1, this u1 plus mu double partial of u2 with respect to x1 x2 plus mu double partial of u3 with respect to x3 and x1 will be equal to density times double partial of u1 with respect to t1. So from the previous slide we simplified it, we actually grouped the similar terms together and then we use this operator, and that can be again simplified. So we can see some similar terms here. So these terms, this term and this term, we can group them together. So that will give us mu partial with respect to x1, and then we can put it so. So what we did is, so this term and this term we combined it, and we are left with the one more term, rho second partial of u1 with respect to t. So as you know, these are the definition. So what we can do is, again we want to simplify. So basically what we are doing here is, we want to simplify the expression, and we want to get the expression in terms of the operator, this operator, and also the dilatation delta. So this term, you know, is delta. So from here again we can combine this term and this term. So because this lambda and this mu, and this part is similar with this, you know, this from here we took this, and this entire thing also give us the same thing, because that is delta. This is equal to delta epsilon 1 plus epsilon 2 and plus epsilon 3. So this plus, we have a second term mu with this operator, and finally we get this expression, the T2. Oh sorry, I missed the U1 here. So similarly this is for only x1 direction. Similarly we can get for x1 direction. Similarly we can get it for y1 and sorry, x2 and x3 as well. So we will write these equations again. So whatever we found in the last slide is lambda plus mu partial of delta with respect to x1 plus mu with this operator u1 is equal to rho second partial of u1 with respect to t2. So this is for x1 direction. For x2 direction we can have lambda mu the same, but with respect to x2 mu u2 and rho second partial of u2 with respect to t2. Similarly for x3 direction we can write here u3 and then second partial of u3 with respect to t. Now these are called equation of motion. These are equation of motion for an isotropic elastic body, and the body forces are absent. Here body forces absent. Body forces means gravitation and even the moment. So both are absent, and so what we will do is these equations, so these three equations we will be using to develop the equation of propagation of elastic wave in continuum. So in continuum, here we will be we are doing for infinite or unbounded media, unbounded or infinite medium. So how we will do it? We will replace the displacement from these equations by strains, and we can group some of the equations together. So what we will do is here is if our earlier equations, if we see these equations, so let's say we call these equations as A, B and C. So these equations, what we will do here is to get the wave equation. So the equation A will differentiate with respect to x1, partial derivative with respect to x1. Similarly with the equation B with respect to x2, and the equation C with respect to x3. So this will give us this expression. So this is the expression, whatever we did it for this partial derivative with respect to x1 for equation A, and then similarly partial derivative with respect to x2 for equation B, and then partial derivative with respect to x3 for equation 3, and similarly in the right hand side also we can have this bracket here. So we have with respect to x1, with respect to x2, and with respect to x3. So if you want to simplify it more, so we are actually operating with the partial derivative. That means so that gives us a second partial of delta with respect to x1, then here again second partial of delta with respect to x2, and similarly second partial of delta with respect to x3. So this expression we want to simplify more. So you can see that we have did some more changes here. So what we did is so nebula is now outside here, and then the earlier it was written as mu partial with respect to x1, and with the operator, sorry, this is u1, and then entire term we have rewritten like this, and these terms are combined. And so what we can do is now we can replacing the displacement by strains. So as you know, the displacement we can replace it like this: partial of u1 with respect to x1 will give you epsilon 1 partial of u2 with respect to x2 will give epsilon 2 and then partial of u3 with respect to x3 will give epsilon 3. So if we replace, if we substitute, so what will happen is lambda plus mu double partial of delta with respect to x1 mu with the nebula operator we have epsilon 1 this is one term here, and then lambda plus mu double partial of delta with respect to x2 plus mu with a nebula operator epsilon 2 plus lambda plus mu, this is delta with respect to x3 plus mu, again it will be similar with 3. Okay, this will give you on the right hand side rho double partial with respect to dt, that epsilon 1 epsilon 2 epsilon 3 double partial second partial of this with respect to time, and then grouping similar terms we get that lambda plus mu, this will delta this is x1 plus this x2 double partial of this x3 plus mu epsilon 1 2 and 3 is equal to rho epsilon 1 2 and 3. So now if we use this delta and this nebula operator, so we can get from the previous equation, what we can get is lambda plus mu with the nebula operator and delta, plus nebula operator with delta rho second partial of delta with respect to t. So which can be, again we can rearrange, and that will give you double partial of delta with respect to t is equal to lambda plus twice mu, both are lem is constant, divided by your density, the nebula operator with delta. So this is the equation for longitudinal wave. This is the equation for longitudinal wave in an unbounded or infinite elastic medium. So this is like elastic wave, we are talking about longitudinal wave. So this unit, the dimension of this term is distance per times whole square. So you can check that term. So dimension is distance divided by time the whole square, and the velocity. So you know that this is analogous to the equation we derive for wave equation of a string. So for a string we derived earlier, the wave equation is what, that it's something like that, whatever we derived, and so this also looks similar, and from here we can tell that the velocity of the longitudinal wave wave is v, longitudinal is square root of this ratio lambda plus twice mu divided by rho. So, this is the velocity, and this is also often called as a bulk sound speed velocity of longitudinal wave in that is elastic wave in an infinite media. And if we use the relation between the Lami's constants and Young's modulus and Poisson's ratio, so mu will be equal to E divided by 2 1 plus nu. So, E is the Young's modulus, nu is the Poisson's ratio, and similarly lambda is equal to nu E Poisson's ratio multiplied by Young's modulus divided by 1 plus nu and multiplied by 1 minus twice nu. So, now that V longitudinal, the wave velocity, can be expressed in terms of Young's modulus and Poisson's ratio. This will be equal to 1 minus nu divided by 1 plus nu, 1 minus twice nu, and here E by rho, the entire thing we need to take square root. So, ultimately if let us say for metal we assume that Poisson's ratio is 0.3, so which will give you 1.346 E by rho square root of the whole thing. So, that means the longitudinal wave velocity depends on the Young's modulus and the density. And if you see for different materials, for air it is 340 meter per second, and if you see if you check for some material like beryllium, so which has low density but high modulus of elasticity, that wave velocity will be very high, 10,000 meter per second. So, we will this is longitudinal wave velocity. We will check that for some other materials also later, but this we can tell that for air it is very low. It depends on the Young's modulus and the density, but for beryllium it is very high. So, what we have derived is the longitudinal wave velocity for infinite medium is square root of Lami's constants lambda plus twice of Lami's constant mu divided by mass density. And we know for finite medium for example the Split-Hopkinson pressure bar, that is uniaxial case, uniaxial stress case. So, the velocity which you write is the C naught, which is the longitudinal wave velocity, is expressed as E by rho. Now, we want to know these similarity between these two wave velocities. The first one is for infinite or unbounded medium, and the second one is for finite medium, which is the case of a striking bar hitting a long cylindrical bar, that is uniaxial stress case. So now we will see the similarity between these two. So for that, what we will do is we will consider the case of uniaxial strain. Earlier in the finite media, for let us say for split Hopkinson pressure bar, we use we considered this a uniaxial stress, but now we are considering uniaxial strain, which means epsilon 22 equal to epsilon 33 equal to 0, only epsilon 11 strain in the one direction is not equal to 0. Now from stress strain relationship, epsilon 11 will be equal to 1 by Young's modulus sigma 11 minus Poisson's ratio multiplied by sigma 22 plus sigma 33. But here we know that we will consider here sigma 22 equal to sigma 33. We will consider this because it is only uniaxial strain, and the other two direction stresses are equal. So then the earlier expression will be epsilon 11 1 by E sigma 11 minus twice sigma 22. So we have removed sigma 33 and we are writing it in terms of this twice multiply 2 times of Poisson's ratio multiplied by sigma 22. We have removed sigma 33 and we are writing in terms of only sigma 11 and sigma 22. And similarly, so epsilon 22, which is equal to 0, but the expression for epsilon 22 is 1 by E sigma 22 Poisson's ratio times sigma 11 sigma 33, and this gives us sigma 22 is equal to nu 1 minus nu sigma 11. So if we replace the sigma 22 in the earlier expression of epsilon 11 with whatever we got here, so then the expression will look like sigma 11 1 plus nu 1 minus twice nu Young's modulus times 1 minus nu. So if you want to know the ratio of normal stress and normal strain in the x1 direction, then that will look like 1 minus nu 1 plus nu twice nu, which will be, so the ratio of normal stress and normal strain, which is the equivalent elastic modulus for uniaxial strain case, uniaxial strain. So now As we know that for a finite medium, that's what for a uniaxial case, uniaxial stress case, so the V longitudinal is expressed by E by rho. Now in this case, for uniaxial strain, if we want to express in a similar fashion, so E bar, which is the earlier expression we got, by rho, and that will be equal to 1 minus nu multiplied by elastic modulus 1 plus nu 1 minus twice nu multiplied by rho. So if we check the earlier expression, in the case of the earlier expression what we derived in case of infinite medium is exactly the same expression, and also we expressed it in terms of lambda and mu as well, lambda is constant, but we actually derived the same expression earlier. So that means for infinite medium, or we can write longitudinal wave velocity in infinite or unbounded medium takes the same expression. So that means now we have a connection, and we can say that this is can be considered as a uniaxial strain case, because we have derived it that the equivalent elastic modulus for uniaxial strain has this expression, and if we incorporate this expression into square root of ratio between elastic modulus divided by density, then we will end up with the same expression of longitudinal wave velocity, and that means that we can consider it as a uniaxial strain case. So next we will discuss about shear wave velocity. What we discussed earlier is the longitudinal wave velocity. So shear wave velocity or transverse wave velocity is shear wave or transverse wave has the dilatation equal to 0. The dilatation term dilatation is equal to 0, which means dilatation is epsilon 11, epsilon 22, epsilon 33, so that is equal to 0. And earlier we had the expression for that equation of motion, which is lambda is constant lambda plus lambda constant mu, partial derivative of dilatation with respect to x1, mu with the operator nebula, this is u1, and is equal to mass density second partial of u1 with respect to t. So this is in x1 direction, So if we take the dilatation delta equal to 0, so if it is 0, then we will end up with mu with this expression, we will end up with this expression, and similarly for other two directions we will have and for third direction so now if we compare with the our earlier derivation, so we will find that the velocity, shear wave velocity can be written as V shear is equal to mu by rho. So, earlier for longitudinal wave what we found is for longitudinal wave our equation was looks something like this. It looks something like this, and from there we evaluated the our longitudinal wave velocity as this, and similarly in this case for shear wave velocity we can say that this is the square root of the ratio of Lemmy constant mu divided by mass density rho. So, this is the shear wave velocity, and we will see different wave velocities of different materials in a short while. So, for shear wave velocity, longitudinal wave velocity for different materials, but before going to that we will also see about surface or Rayleigh wave velocity. Oh sorry, this is I wrote the rho but it was somehow erased off. So, this is rho lambda by twice mu divided by rho, and that next line is correct. So, we have rho here. So, the derivation for Rayleigh wave velocity is not included here. However, we will just show the ratio of Rayleigh wave velocity to shear wave velocity. So, K, the ratio is Rayleigh wave velocity V Rayleigh by V shear is K, and then K can be found in the cubic equation in K square. So, it is a complicated equation. It looks a little complicated here. So, this is the equation, and where alpha 1 square is 1 minus twice nu divided by 2 minus twice nu, and this will come out to be V Rayleigh is equal to 0.862 plus 1.14 nu divided by 1 plus nu times shear wave velocity. And if we assume Poisson's ratio is 0.3, which is for most metals, then V Rayleigh is 92% of shear wave velocity. So, that is the relationship for nu equal to 0.3. So, V really is just 8% lower than the shear wave velocity. So, next we will see wave velocities of different materials. So, here are some common materials like copper, metal, aluminum, iron. They are very commonly used materials, and then alumina is like the ceramic, Al2O3, and then a very hard material, diamond. So, if you see the Young's modulus for copper, it is 130, and then the density is 8930. If we talk about different wave velocities, we have not included the Rayleigh wave velocity here, but there are two types of longitudinal wave velocity we included here. One is the thin bar, that is for a finite medium, and then second one is the infinite body. If you can see, the thin bar has 3812 meter per second, that means almost kind of 4 kilometer per second, 3812 meter per second. So, infinite body, it has 4.7 kilometer per second, and then shear velocity is 2325 meter per second. Similarly, for aluminum, it has a lower Young's modulus and lower density. So, it will result, however, a higher longitudinal and shear wave velocity. For iron, it has a higher Young's modulus and higher density. However, those longitudinal wave velocities are very much similar with the aluminum. If you can see, they are very much similar with aluminum. Now come to the ceramic, which is quite high strength and low density. This will give us a very high longitudinal and shear wave velocity. So, this is very high, 11 kilometer for infinite body, 11 kilometer per second, and for diamond it is even higher because the Young's modulus is unusually high and then density is quite low, and then this gives us for a thin bar it is 16.8 kilometer per second for a thin bar. The others we haven't kept the values here. So, that is all about wave velocities. We derived the expression for longitudinal wave velocities in continuum, that is infinite, medium or unbounded medium. We also mention about the shear wave velocity expression, and we talked a little about the Rayleigh wave velocity as well. We also listed some of the materials wave velocities with their Young's modulus and density values. So, that is all for this lecture. Thank you.